So last time we stated Mayer-Vietoris, and so Mayer-Vietoris says that if you have some manifold M, which is decomposed into two different parts, so this left part is M1 and this right part is M2, and the intersection M1 intersect M2, I'm just going to call M12 for short. Then we have some maps over here which says M1 includes into M and M2 includes into M, so I'll call those maps I. And then the intersection includes into each of the pieces, so I'll call those maps J. And we just discussed last time that if you have a map from one space to another space, then you can pull back a differential form, and this is essentially a change of coordinates. And after that, I stated this theorem, which says that there is a long exact sequence associated to such a decomposition, which looks like H0M to the direct sum of the two pieces to H0 of the intersection. And then there's this funky boundary map, which we'll talk about, going to H1, and then H1 the sum, H1 the intersection, going to H2, and so on and so forth. The maps over here are, the map from H0 to H0M1 is the pullback and the inclusion of M1 in space, similarly for M2. And this map over here is take the two inclusions of M12 into these two spaces, pull back along those, and take the difference. So exactness over here essentially is saying if you have two different forms on these two different pieces which agree on the intersection, then you can glue them together to get a form on your whole space. And then this co-boundary map we'll talk about along the proof. So any questions on the statement of the theorem? Anything you would like to review? If not, we can get started, and then if you have anything, we can discuss. All right, so in order to prove this, by the way, I just say it to you. What's the idea of this theorem? It's like, we computed cohomology in very special cases, like looking at some very particular differential forms in the first problem set, but that can be difficult to do in general because, as we discussed over manifolds, even defining a differential form is really difficult. So it's like, how do we even compute the cohomology of a space? So the idea of Mayer-Vietoris is break your space down into smaller spaces that you can stick together. And intuitively, maybe you can think like, if you understand how the holes of one space and the holes of another space and how these two spaces fit together, you should be able to understand the holes of the space as a whole. So that's the idea. This guy is like building up a space from smaller subspaces and then being able to compute cohomology sort of algebraically through that. So for the proof, first we're going to need to look at something called chain complexes. So a chain complex is a sequence of spaces with maps between them, similar to an exact sequence, except it has a bit of a weaker condition. So I'll just write the chain complex that most concerns us. Like 0M to 1M to 2M and so on. And all these maps are the exterior derivative. And so a chain complex is a sequence of spaces like this with maps between each space. And I guess this map would just be the inclusion map. And the point is that if you take the composition of two of these maps, you're always going to get 0. So this is with the condition that d squared equals 0. And we saw that this is necessary. For example, if we want to define cohomology, we need like the image of one of the d's to lies in the kernel of the next one, so this is that condition. This is similar to an exact sequence, except in the exact sequence we dictate that the kernel of this map is exactly the image of this, but this is not exactly the same thing. This just says that the image of this is contained in the kernel. So it doesn't have to be the whole kernel, it just has to be contained in it. So it's a weaker condition, and we saw the cohomology is the kind of the failure of this guy to be exact. And so, you know, category theory. We have objects, chain complexes. We also need maps between objects. So what happens if you have a map from N to N? Well, then you get induced maps from omega k and if I call this f, the induced maps f star back to omega k m. And again, this is like restricting to a subspace or change of coordinates or whatever. So you have induced maps like this. And so if you have a second chain complex, which is the chain complex of differential forms on n, then what you're going to have is maps going along this way, which is f star, right? And crucially, there's this fact that D composed with f star is equal to f star composed with D. So what does this mean? This means that if you take the exterior derivative and then you apply the exterior derivative and then you pull back, it's the same thing as first pulling back and then taking the exterior derivative. And if you sort of, I'll leave this for you to think about. You can either do it computationally by writing out all the formulas and checking that works, and this is essentially a like change of coordinates formula again. Or alternatively, you can sort of think about this at a highbrow level of like what we're doing with Stokes' theorem. And what this is saying is that your function f is compatible with Stokes' theorem on both sides. So if you like compute an integral on the right, you can pull that back and compute the integral on the left, and you get the same answers. Questions on this, or do you want me to explain this more? Yeah.
Can you explain what you meant with the Stokes theorem thing?
Yeah, so let's say that like, this is your space n, right? And let's say that you have like a disk D with the boundary S, okay? And this maps to M. And let's say that you have some differential form omega on M, right? So we know that the integral over f of s of omega is equal to the integral over f of d omega, simply because this is f of s, and so this is f of d. So the boundary of f of d is f of s, right? But this is the same as a statement that the integral over s of f star omega, which is saying that like pull back the different form and then integrate over here, is equal to the integral over d of d f star omega. So this is from Stokes' theorem. But then by this equality, this is equal to the integral over d of f star d omega. So this says that, can I look at Stokes' theorem on this manifold, and then that'll give you this guy. Or you can look at Stokes' theorem on this manifold and then pull back, and that'll give you this guy. So that says applying d after f star is the same as applying f star after d. Make sense?
Yeah, I think so.
Okay, so now remember that we define, wait, so there's a, if you haven't seen it, there's a way to think about this using, they call it commutativity, and it's commutativity because you can like flip the order of the maps. But the way I like to think about it is like, if you want to get to, say like, if you want to get from here to here, then you can just like apply a bunch of these maps. And commutativity says it doesn't matter what order you apply the maps in. So you apply D, D, F, or you apply D, F, D, or you apply F, D, D, and you're going to get the same answer regardless. So any of these two spaces, you can sort of follow different paths and you get the same answer. And if that happens for such a thing, that's called a commutative diagram. So my claim is that if you have this sort of statement, then you get an induced map on cohomology. So this induces a map f star from HKM to HKM. So there's some things to check here. Remember that HKM is defined as the kernel of D modulo the image of D. So you have to check some things. First off, if you have something which goes to 0 over here, and you pull that back to n, does it go to 0 over here? Right? Because that tells you that this map is well defined. Because something goes, this is defined as like an element of HK is some equivalence class of omega. So this is like omega plus eta, such that d omega is equal to 0, right? So the first thing you have to check is like, okay, is this condition still satisfied if we take this map? Can someone tell me why this is true?
So we have an omega, right? We apply d to it and it's 0, which means if we apply f star, it's going to be 0.
F star here is going to be 0?
No, after applying d.
After applying d, it's going to be 0.
It's going to be 0. And then that means if we take the other path, it also has to be 0.
Yeah. So this says that because this goes to 0, then if you map 0 to something, it's going to be 0. So this says that if you first pull back and then take d, then it's still going to be 0. So this says that this implies that d of f star omega is equal to 0. But let's say that you had another representative, omega prime, right? So if you had another representative, omega prime, then it's equal to omega plus d eta. So why should f star omega prime equal f star omega?
They differ by d f star eta.
Yes. So here, if this is true, then this means that f star of this is equal to f star of this, and this is equal to f star of omega plus f star d eta, and again you can swap these two, so this is equal to d f star eta. Any questions on that? So this tells you that if you have a map between manifolds, and that induces a well-defined map on cohomology the other way around. Yeah, so I guess as an example, we saw, again, I mean like a differential form is not a vector field, but you can kind of cheat and think of it like a vector field. So we saw like this vector field that like generated this whole center, right? So if you take a circle, we can map it to this guy along this. And this says that this generator of H1 restricts to some element on the circle. Now whether or not that element is trivial depends on this map. So if this was the map from the circle to R2, then the pullback would be trivial. But if this is the map to R2, the pullback turns out to be non-trivial. Any questions on chain complexes, pullbacks, cohomology? Okay, so now we've seen chain complexes, we've seen exact sequences. Let's talk about an exact sequence of chain complexes. Okay, so this whole line that I just erased, shorthand for that is omega star m. So this means like the entire thing, omega 0, omega 1, omega 2, and all that. So this maps via I1 star, I2 star to omega star m1 plus omega star m2, and this maps via j1 star minus j2 star to omega star m1, 2. Okay, so when you write exact sequence like this of chain complexes, what this means is that this holds degree by degree. So this means that omega 0 maps to omega 0 plus omega 0 maps to omega 0, and then omega 1 maps to omega 1 plus omega 1 maps to omega 1, and all those sequences are exact. That's what an exact sequence of chain complexes means. And so why should this be true? Again, exactness over here is not that deep. It says that if you have two differential forms over here which agree on their intersection, which you're measuring by pulling back to the intersection to take their difference, if that maps to 0, that means that j1 star of this guy equals j2 star of this guy, so they agree on their intersections, that means you can pull it back to this. Saying that this map is injective amounts to saying that if the restriction of some differential form on each part, if both of those are 0, then your differential form itself had to be 0 to begin with. And so this part is a bit more technical. So do anyone have questions on why it's exactly over here and over here.
You repeat what you said for the middle one?
Yeah, so this says that, let's say that you have tau comma eta, which maps to 0, right? This means that J1 star tau is equal to J2 star eta, right? So this means that we can define some omega over here, which is defined as tau, or like omega sub x is defined as tau sub x if x is in M1, and eta of x if x is in M2. I guess I'm kind of being like loose with this, but what I mean by tau sub x is like a function on the tangent space. And this is well defined because if you look at the restrictions, they're the same. Does that make sense?
Yeah.
Okay, so now why is this surjective? So you look at like, this is like, I think one of the cool things about the differential forms approach to cohomology is that you can like use some tricks from like, use some analytical tools which you don't have access to if you're like doing singular cohomology or something. So if you have seen this proof before, like there will be some things which are a bit more different because there's some things which you can talk about a bit more explicitly. So this surjectivity will be one of those things. So if you have a form over here called omega, right? Question is, how can we get two forms over here such that their difference is omega? Anyone have any ideas? So we're looking for a tau comma eta such that J1 star tau minus J2 star eta equal to omega. Yeah.
Can we make one 0 and the other one omega?
Okay. So let's think about that. So let's say that we have our line segment as a whole space, right? And these are two guys. So let's say that you have omega defined on the intersection, right? So you're suggesting let's put 0 over here and then set this one to omega. So omega is defined on this. So how should you define it on the outside?
0.
Okay, so let's say that if we like graph this, if you can make some sense of a graph, this is some non-zero thing, right? If we extend it to a non-zero function on the outside, is there an issue at this point?
Does seem like it, yeah.
So it's not smooth at this point, right? So extending it to 0, just naively, doesn't give you a great answer. But it is a good idea. So the idea is, how can we extend this to 0 over here? So if we want it to be smooth, right, then we should have it so that like, maybe it's like omega in the middle, but like near the end it cuts off to 0, right? And over here, the thing is like, now this doesn't restrict to omega, right? But we have to use the fact that we also have this other space. We just set this other space to 0. So what we can instead do is have something which goes to 0 over here, and out here comes up a little bit, and then like fixes this part. So that if you add up these two things, you get omega back, but like this goes to 0 on the right, and this goes to 0 on the left. So the question is, how can we make that work? And the idea is that we can use a partition of unity. I think in the previous lecture I gave the definition, so I won't do that again. So if you have a partition of unity subordinate to this cover, then essentially that amounts to having functions phi1 and phi2, such that support of phi1 or phi is contained in mi. Right? So here's a question. Using these partitions of unity, how can we find a form that's related to omega, but extends to 0 on all of M1, outside of the intersection?
Phi1 times Phi2.
Phi1 times Phi2, okay. How are you going to relate this to omega?
And then I'll multiply by omega.
Multiply this by omega, okay. That works. Can you come up with something a bit simpler? How'd you come up with phi1 times phi2?
Phi1 is has support contained in M1, right?
Yep.
And phi2 has support contained in M2.
Yep.
And we want something contained in their intersection. We want something.
Well, you already have something contained in the intersection, and you want to extend it from the intersection into M1. Right, so what we're starting with is this, and what we're trying to find is this guy.
I see. Oh, I misunderstood. I thought you wanted something whose support was in the intersection.
Right, sure. So what we're starting with is something in the intersection, and what we want to do is extend it to this left part, M1.
Sure. I mean, we can always do phi1 times omega.
Okay, so phi1 times omega. So,
It seems
when
like, should we do 1 minus?
okay, yeah. So why 1 minus?
Because we want it.
This is like
We want the opposite of what the picture looks like. We want it to become more omega at the
on the intersection, right? So phi1 kind of goes to 0 on the intersection, and phi2 goes to 0 on the intersection from this side, and it sort of like caps out at 1 over here, and this one caps out at 1 over here.
Right.
So you can do 1 minus that, and so you get something that goes like 0, and it has to be 1 on like M1 minus the intersection, because like the sum of phi1 and phi2 has to be 1. And so it'll slowly like increase and do something like that, right? Yeah, so is there another name for 1 minus phi1?
No.
What condition on phi1 and phi2 do you have?
But their sum is 1,
Yeah.
so it's a phi2.
Yeah. So this is phi2 times omega, right? So, to recap, let's say that you have something on omega. So you have some partition of unity which looks like this. So pretend like the sum of these two functions is always 1. This is phi1, this is phi2, this is on M1, this is on M2, and this is their intersection, M1, 2. So what you can do is you can extend this omega, whatever it is, to the entirety of M1, multiplying not by phi1, but by phi2. So phi2 omega lives inside M1, right? So what lives inside M2?
phi1 times omega.
Phi1 times omega. Okay? And how can you, if you have these two guys, how can you recover omega?
Take their sum.
Right, so phi1 omega plus phi2 omega due to omega, and that's because phi1 plus phi2 due to 1 everywhere. Okay? So how should you define tau and eta?
Tau is phi1 omega and eta is phi2 omega. Wait, but we need it to be a difference, so we should add a negative sign.
Yes. So what should tau be?
Phi1 omega,
Yep. Phi1 times omega, and eta should be
negative phi2 omega.
negative phi2 omega. Does anyone have questions on this? Does anyone not see why we did this? Everyone good with?
Actually, what's the support then?
Ah, yes. Support is the set on which a function is non-zero.
Okay.
So this is saying essentially like, the point of partition of unity is like you have something, if you have a function on like a whole manifold, right? We can't understand a whole manifold, we can understand like different small pieces. So we want to have functions which are non-zero only on those pieces. And what we can do is we can, such that the sum of all of them are 1. So if we have some sort of a function like thing f, we can create these functions fi, which is equal to phi of f. And so these have the property that the sum of fi is equal to f, because the sum of these guys is 1. And it also has the property that these are non-zero outside of some open set. So you can understand them just by looking at that open set and ignore the rest of the space. Is that good? Cool. Okay. So now the proof of this thing. How do I write this out? Okay. So let me do an I over here. And then we still have our exterior derivatives. which take us to omega I plus 1 with m omega I plus 1 of m1 plus omega I plus 1 of m2, which goes to omega I plus 1 m1, 2. And you have zeros, because again, this is injective, this is surjective. And these are the exterior derivatives, right? And you have maps going out of these and maps coming into these, which are coming from the previous differential forms and the later differential forms. So these, like I said, these are maps between chain complexes, so it induces maps on cohomology. So what that means is you get induced maps Hi M1 plus Hi M2 to Hi M1, 2 and Hi of M. So this forms part of our exact sequence. This forms this part, right? However, yeah, so exactness over here is exactly the same thing that we've been saying all along. These are equivalence classes of some differential forms. And you have to check that if these two differential forms, there's a little bit to check where, since it's like an equivalence class, essentially the idea is, again, like if the restrictions are the same, you can pull it back to a different form in the whole space. But the thing is, all you know because of this is that if you have tau comma eta, like equivalence classes of these forms, then this goes to tau minus eta. I won't write the J stars, I mean the restriction and then take the difference. And we know that, we want to say that if this is 0, then it goes back to here. But if this is equal to 0, then that doesn't necessarily mean that tau minus eta is 0 on the dot. It means that tau minus eta is equal to d of some other form psi. So what you need to do is sort of like use this psi, use that same thing that we did with the partition of unity, and use the psi to modify tau and eta, such that the difference of these two guys is 0 on the dot, and you can glue those together. So maybe we can talk about it later. For now, leave it as an exercise. What I want to more talk about is like the failure of exactness on the ends and how we can fix that. Does anyone have any questions on like, does anyone not believe that the middle is exact on vibes? Okay, so what's the problems on the ends? So again, I'll just keep writing this out because I feel like when you're starting off, it's like hard to remember what this is defined as. Just the kernel of B, modulo B into B. And again, elements are equivalence classes of phase, such that d omega is equal to 0. Okay, so why does exactness fail on the ends? So I claim this map is not necessarily surjective and this map is not necessarily injective. So what happens here is, let's say that you have a differential form over here. Let's call it omega, right? You know that this comes from some differential forms on these guys, right? So omega over here as a literal differential form comes from some tau and eta over here. But the point is, tau and eta may not satisfy that d omega equals 0. Sorry, d tau and d eta is equal to 0. So what that means is that the differential forms here may not represent cohomology classes over here. So this map is not necessarily surjective. On the other hand, let's say that you have, yeah.
Could you draw a picture of them? So is there a picture for that?
Mm-hmm. Give me a second. Yeah. Maybe let's work on an example of how to compute with this, and then so that way you can actually like see what's going on. So let's say that you take the circle, right? We want to compute the cohomology of the circle.
Okay.
What do you expect the cohomology to be for itself?
R.
R in what dimension?
1,
In dimension 1, what about other dimensions?
0. Or
Uh,
the 0th dimension.
R in the 0 dimension, R in the first dimension, right? Because it 0 dimension measures connected components. 1 dimension measures circles which can be contracted to disks. So yeah, you expect that to be zero, right? So let's take M2 to be this lower semicircle and M1 to be this upper semicircle, right? So M12 is equal to this guy and this guy, right? Okay, so let's work out the exact sequence. So so it starts off with 0 over here, H0 of M, H0 of plus H0 M2 goes to H0 M12. And this will go to H1 of M, and I don't think that's math. Okay, so M1 is equal to this, and M2 is equal to this. Okay?
Right.
Okay, so what is H0 of M1?
R.
R. What's H0 of M2?
R.
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 And what's H0 of M12?
R squared.
R squared, because there's two connected components. Right? So now, is there any other things in this column or this column that will be non-zero?
Don't think so.
No. So it's because of the theorem that I haven't stated yet, which is that HK of Rn is equal to R if K equals 0 and 0 otherwise. So there's one kinetic component, there's no holes. Makes sense. And this is like homeomorphic to copy of R, this is homeomorphic to copy of R. Another theorem I haven't stated is like if you have homeomorphism, this falls from like if you have two manifolds and homeomorphisms between them, then that induces maps on chain complexes, which induce maps on cohomologies, such that if you compose both of them, you get the identity. What that amounts to is if you have two manifolds which are homeomorphic, they have the same cohomology, which is what we should hope for. So what that means is that you have R's over here and nothing else this way. Okay, can you tell me anything about this column that you know a priori?
H0 of M is R.
Yeah. Why do you know that?
Because there's one connected component.
Exactly. So there's one connecting component of H0, there's one connecting component of M, so H0 of M is R. So what this says is that this is injective, right? So this has a multiple of R as a copy, the image over here, right? So what is the image from this R2 to this R2?
Zero.
Why?
Because it's like a diagonal map that I'm taking a difference in.
Okay. So you're trying to like explicitly do this. So I'm saying like just think about the fact that this is exact, right?
Oh, okay, sure.
So this is a map from R to R2, which is injective. So what is the next map? What's the image of this map?
The kernel, that's one.
Yeah. What's the kernel of this map? I guess
Oh, which map? This map?
this one.
The image of the other one.
Yep. And so what's the image of this?
R.
R. So you're taking two factors of R, killing off one factor of R, right? So what's the image over here going to be?
R.
Like right now would be right. If you kill a copy of R and you have two-dimensional space. Okay. So then the image of this guy is R. So what's the image of this guy going to be?
Is it also R?
Correct.
Yeah.
So the image of this R2 into this map is also R. So this is an example of something where here you have things over here which don't lift to this. So what's an example? Something which takes a value of 1 over here and something which takes a value of 0 over here. Why? Because like if it were to come from these guys, well this guy is a constant function on the upper hemisphere, right? which means that it has to take the same value on both ends. Same with this guy. But it's impossible to take the difference of two things which take the same value on both ends and get something with different values from both ends. So the image of this map over here is things where you have A, so like the same thing on both sides. And then the co-kernel is anything with two different values.
And they have to be constant because
They're coming from the image of this. And
Potential zeros.
right, because they're closed.
yes,
Makes them constant.
Yes.
And that's why we could pull them back to differential forms.
on here, then it would have to be constant on this whole thing.
But if we didn't need them to be closed, then we would have.
Yes, then you can take something which is like 1 over here and like goes down to 0, and then again like 1 over here and goes down to 0. You can do the same partition immediately trick.
That makes sense, okay.
Okay,
That kind of makes sense.
sure. So let's say now, why, so this one's not necessarily surjective. Why is this one not necessarily injective? Let's say that we have omega and omega prime over here, right? These are two different cohomology clusters over here. If you look at their images, right, what happens is, first off, you need d omega equals 0. That's why this one wasn't surjective. But you also are taking equivalence classes of things, which means that you are identifying things together which weren't identified over here. So maybe omega and omega prime, you know that they map to different things on this level, right? So if you have omega and omega prime, then these two map to two different things over here. But after taking these equivalence classes, it might end up being that these two get sent to the same thing over here, because the two forms end up being equivalent up to addition of d of something before. Does that make sense? So you have a failure of injectivity, you have a failure of surjectivity over here coming from d omega equals 0, and a failure of injectivity over here coming from the fact that we're taking equivalence classes. So if we're trying and study these two things, it turns out that somehow both of them like arise from the same thing. Like there's a way to relate them together, which I think is pretty cool. So, any questions on the example? I accidentally erased it. So if you do, we'll wave our hands. Yeah, so what happens? Let's try and analyze this more carefully. So let's say that we take some omega over here, which this does not surject onto, right? What can you tell me though on this level?
On which level?
On like the level of differential forms, not going into cohomology yet.
Yeah, it has a.
Yeah, so it is surjective on this guy, right?
Yeah.
So there is a pair tau and eta such that their difference is omega. But what do you know about tau and eta now, because omega is something which this is not surjective onto?
They're not closed.
They're not necessarily closed. So what we can do is we can check, okay, what is the failure of the closure? Of closure isn't a good word. I guess people say closure, no one ever says closure. What's the failure of this guy being closed? And so we can measure that by just looking at the d of it, right? Should we look at d tau and d eta, right? So we have 3 vertices of a square. What should the fourth vertex be?
What?
So we know this guy, we know this guy, we know this guy. I'm claiming it would be really helpful if we knew what this guy is.
D omega?
Right, so there should be d omega. What can you tell me about d omega? From the fact that it comes from a cohomology class.
0.
Right, so d omega is something which is closed, so it's 0. So what that means is by commutativity of this diagram, the difference of these two should also be 0. Now what can you tell me on the level of differential forms here? If you have two things which go to 0 when you take their difference.
Then they're the same? Or?
Not quite the same, but what does exactness of this row tell you? So like you have two differential forms which agree on the intersection, and that means that on the whole space you can
make a, yeah,
Glue
there's
them.
something, they're in the image of the previous map.
Right, so you can glue them together to get something which I'll call delta omega. So there's something called delta omega which maps to this guy, and then this guy measures like the failure of this to be closed. And the failure of this to be closed exactly measures the failure of this to be surjective. So that says that if you have some omega over here, what you end up getting is some delta omega over here. And you can check, you can read any book, I don't feel like going over the details, that this is a well-defined thing in the sense that if we choose, there's some choices we made here, right? We chose like different lifts. We chose like lifts of this omega. We chose a representative omega of this cohomology class. And we chose this lift over here. You can check that the cohomology class resulting from this is independent of all of those choices, which doesn't necessarily mean that you get the same exact differential form here. That means that if you like make some other choices and you get like some other differential form, then the difference of these two will come from up here. So you can sort of check through some of those cases and make sure that that works. But what that tells us is that if we have a differential form over here, omega, then what we end up getting is a differential form delta omega on hi plus 1 of m. Any questions on the formal algebraic thing that we just did in order to show that this is true? Okay. So now, this is, I think, where differential forms are nicer than singular cohomology. Because in singular cohomology, you're like, we have proved this theorem, and now basically you can only do algebra with it, and there's like no intuition about what this co-boundary map is. This map, I'm gonna call it co-boundary map. But in differential form land, you can actually come up with a nice interpretation for this. So the exactness at this point is pretty geometric, right? But like what this map even is not so clear. So what you can do is we can actually like work with our special lifts that we found earlier and describe this map pretty explicitly. So as a reminder, if we have omega, how do we get some tau and eta? Okay, so what should tau and eta be?
P2 omega.
P2 omega.
Negative P1.
Negative phi 1 omega. Right, and again, that's so that their difference is phi 2 plus phi 1, and this is supported on phi 1, and this is supported on phi 2. Okay, so what's the next step in our procedure of constructing the co-boundary map?
Take the differential, exterior derivative of each thing.
Yeah, so we take d of tau, and this is equal to d of phi 2 omega. Let me write something over here. D of, do we need this right now? Wait, let me write the special case first, and then we'll talk about the general case later. D of f omega equals d of f times omega plus f d omega, which this follows from like product rule. You can just do out the computation from the definition that we had last time and check that that's true. So this is equal to d phi 2 omega plus phi 2 d omega. Can we simplify this in any way?
Did omega come from
Cohomology class, yes.
The omega is 0.
The omega is 0. Okay, so what should d eta be then?
Negative d phi 1 omega.
Okay, so now from our abstract argument here, we claim that these should be equal on the intersection, right? So, by the way, I guess I like formally wrote out what this multiplication means. What this multiplication means, I guess, maybe you didn't think about what the multiplication means right now because I've been writing it so confidently. But what it means on the level of like linear algebra is like if you have I think I mentioned this briefly, but it's going to be more and more important as we go on. If you have like two linear algebraic forms like this, then what you can do is you can take the wedge product. And this is like nothing more than like just, you know. So this essentially says like if you have something which measures something in one direction, something which measures the area in a perpendicular direction, and then this measures the volume spanned by those three directions together. So a wedge of a K form and L form gives you a K plus L form. So in this case we have a 1 form and a K form, so we get a K plus 1 form, just like we expect. Right? So, can we see clearly that these two guys are the same? Can you rewrite phi1 in terms of phi2?
1 minus v2.
Sure, so this is negative p of 1 minus phi2. Right? So now, what's d of 1? 0, because it's a constant function. So this is equal to d of phi2 omega. So, and the thing was, right, how you glue it is you just say, okay, if it's on M1, if you have a point on M1, you make it equal to this guy. If you have a point on M2, you make it equal to this guy. And we see that these two guys agree on the intersection because on the intersection, both of them are equal to d phi 2 times omega. Okay, can we see this a bit more graphically? So let's say that this is M. This is the intersection. So phi1 is going to look something like this, and phi2 is going to look something like this, right? So this is the graph of phi1. This is the graph of phi2. So if we draw the derivative of phi2, what happens? So again, this is M, and now we're going to be drawing the graph of d phi1 or d phi2, right? So it starts off, it's 0, 0, 0, nothing's really happening. And then phi1 starts increasing, right? And then, so that means that the derivative becomes positive. But then what happens is that the derivative starts decreasing down to 0 again, right? So you'll end up getting something like a bump function. And similarly, what happens with d phi1 is phi1 starts off constant, so the derivative is 0, and then phi1 starts decreasing, and then the derivative starts increasing again. So d phi1 would be negative of this plot. So we can still, again, see that this is the same. So it's a bit awkward to talk about a graph of a differential form again, because what is a differential form? It's something where you take in a vector and gives you a number, right? So what is the direction along which, one form essentially like dictates a direction, and you're saying like roughly projection onto some direction, right? So what is the direction that we're projecting onto? So what happens is, let's draw a picture more like this. So this is your manifold M, and then this is how you split it off. So let's say that phi1 starts off up here, and then it like goes down to 0, right? And then phi2, so this is sort of phi1, where like more bold places represents positive. So super bold means 1, nothing means 0. And phi2 is going to look something like super bold up to the intersection, and then it'll like taper off to 0 over here, right? So if you look at the derivative, what the derivative is doing is it'll sort of be like a bumpy guy on the intersection of these. So measure the direction sort of like perpendicular to the intersection of the two manifolds. Does that make sense?
What's going on? What did you say at the end there?
So what I'm saying is like you're trying to measure, so the derivative tells you if I move in some direction, how much does it change, right? So if I plugged in a vector that's like vertical into d phi2, it'll give me 0 because like this doesn't really change in that direction. It only changes like transitioning from M1 to M2. So like the direction that's sort of going, or M2 to M1, I guess. So the direction that's going M2 to M1 is gonna be the direction on which this evaluates to something non-zero. So it'll sort of be like a bump function. That's not a bump function. It'll sort of be like a bump function in this direction, and it'll be like 0 in the perpendicular directions. So if we like coordinatize this and we call this like in local coordinates x1 and x2, this will look something like this function times dx1. Does that make sense?
It could change a little bit perpendicular.
It could change a little bit perpendicular.
But
Basically this, yeah. Yeah, so the point is like, I guess, yeah, I'm trying to draw like a schematic of like what is geometrically happening.
In our calculator there, we showed that d eta was equal to d tau. Right?
Correct.
But they should only be equal at the intersection.
Correct, because they're not defined elsewhere.
Right. But
Like d tau is not defined on M2 minus the intersection. So this formal calculation like only shows that it's valid on the intersection. The formula calculation that we did, like calling this and then saying that this is like V2 omega, this only works like on the intersection. Because like simply because these guys aren't defined outside of it. Like this lives on omega k of M1, and this lives on omega k M2. So like they just aren't defined outside of it. But I mean like if they were, like basically what you're doing is like the differential forms, when you glue them together, differential forms are 0 outside, right? And like you know that they go to 0 along like the boundary of the intersection. So in that sense, yeah, they are kind of equal outside, but you just need to check that they're equal in the intersection. Yeah, so what we're doing here is we're taking a differential form and we're essentially multiplying it by a bump form sort of on the transition from M1 to M2, or like I like thinking like on the, like if you have the intersection, then it's like a bump form that's perpendicular to the intersection. So for example, if we look at our circle case, right? So what happens here is, let's say that we have this function which is 1 over here and 0 over here, right? So if we look at, let's call this form omega, and this is, let me just like erase the top and bottom. This is the form on the intersection, which is 1 over here and 0 over here. So what we're doing is or let's say something a bit more interesting. Let's say it's 2 on this side, right? What we're doing is we're multiplying it by a bump form, which sort of moves along this direction. So what it will look like is sort of a 0, 0, 0, 0, 0 here, bump over here, 0, 0, 0, 0, 0 over here, 2 times a bump over here, 0, 0, 0. And so this sort of represents, if you want to think of it in terms of a vector field, like a vector field which starts with small over here, gets like big over here, small goes to like no vectors, small vector over here, bigger vector over here, small vector over here, and goes to 0. And so if we integrate this along the circle, we'll get something non-zero. So you can see that this does indeed generate H1 like we expected. Another picture, we can go 1 dimension up and think about a circle, or a sphere I should say, and take the upper and lower hemispheres over here. And so, let's see here, yeah. So if we have a generator, so what does the intersection look like? The intersection looks like this band, right? And so what can you tell me about the cohomologies of these intersections, of the intersection here? Okay, so it looks like a circle, right? So what should the cohomologies be? R and R and 0 and 1. And this is based on another theorem that I didn't tell you. Is it okay if I erase this? So, HK of M cross Rn is isomorphic to HK of M. This should intuitively make sense because you're not like adding any holes here. And the reason for this is essentially you have 2 maps. So M includes into M cross Rn, right? but this also projects back down onto M. And so if you like compose the pullbacks of these two, if you, so let's see here. If you include this guy and project it back, then you get the identity map over here, right? So that should tell you that if you take pi star I star, then you should get the identity map, the dot, sorry? Yeah, yes. No. You first include and then project.
In the order swap.
Including pulling back.
Yeah. Yeah. So this is pi composed with pi. Yeah. So if you do this, then you get 1, right? But if you project and then include, then you're gonna get like the 0 section. You're not gonna get like the full thing. So you expect that I composed with pi star is not the identity on the level of differential forms at least. What you can show is that, I won't talk about this, but there's something called a homotopy, chain homotopy. And what a chain homotopy is so we said that like, if you have something like this is a chain complex, right? And chain homotopy is something which goes one lower. So this is at position I, this is I minus 1, this is I plus 1. So a chain map is something which goes down, right? Chain homotopy is something which goes over one dimension lower. And what you have is that if dk minus plus or minus kd is equal to f, then you have that f star is equal to 0. This is an algebraic fact. So it says that if you like do d and then compose it with, sorry, if you do d and then compose it with k, plus doing k and then composing with d, if that's the same thing as just doing f, then it turns out that the induced map of f on cohomology is 0. So you can check a reference for that. In the proof of like the Poincare lemma, there's a nice geometric proof which I would like to go over, but I won't because it takes us too far aside, which is why I won't talk about this at all. But this is like the idea of how you prove such a thing. You show that you can construct such a K basically by integrating along the fibers, or something like that. And if you do that, then it satisfies this condition. And so this map is not identity level of forms, but is identity level of cohomology. Okay, that was a bit of a digression. But what we have here is like the generator of this S1, right? It's gonna be some differential form, which like essentially integrates along the radial direction, right? So let's call that d theta. And what should the boundary of d theta be? So this will be something which goes in like h1 of the intersection, right? And then the co-boundary operator will take us to h2 of s2. And we know that like the upper and lower hemispheres are both this, so they actually go cohomology. The intersection is a circle, so it doesn't have any h2. So this will be going to 0. And we expect this to be r. So the co-boundary of this guy should generate this guy, right? And so we can kind of see that because what we're doing is, again, we're multiplying it by a bump form, which is sort of perpendicular, which is perpendicular to the direction. So the S1 part is for keeping track of the radial direction, and this bump form is keeping track of the perpendicular direction. So what you end up with is some differential form which has support only like near the equator. And what it'll look like is looks like d theta. This looks like some like bump form phi times d phi. So in total, what this will look like is some bump form times d theta d phi, which if you integrate that, you'll get some non-zero positive number. And so that shows that this guy is equal to R.
Why, if we have a form that integrates to something that isn't zero, does that mean we have a generator for the cohomology?
So we know that it's non-zero in cohomology because if it was zero in cohomology, that would mean that it's exact. And if it's exact, we know by Stokes' theorem that the integral has to be zero. Because S2 is a manifold without boundary.
Right.
So that's like generally, yeah, so generally, again, like how you show that a differential form is non-zero is find some submanifold that you can integrate along, and if the integral is non-zero, you know that your differential form is also non-zero. Yeah. Any questions?
And we know that this thing is, so we know it's not zero, because then its integral would be zero. So it's not exact, but we know it's closed just because of how we checked our co-boundary. Right? Okay, that makes sense then.
Yeah, I guess, yeah, you do have to check that like this guy's closed. But again, you can like do that because looking at this guy's closed would be like going down and then right? Sorry, it would be going down, right? So this will be like D of del. But then if you go down and right, then that's the same thing as going down twice here. And going down twice here is decomposed with D, which is zero. And because this map is injective, you know that D of this is zero.
Gotcha.
So that shows by algebraic argument that this is zero. If you want to check more explicitly, you can check over here, right? If you take D of this guy, you get D of this times omega plus this guy times D of omega. Both of those are closed. So yeah. So that is that. Try to decide what to do now. I can either start talking about intersections, or I could do another geometry of the day. What would you prefer?
What's geometry?
Remember how last time we talked about like RPN and CPN?
Sure.
Okay, let's do that. Yeah, because I feel like there's like so many examples that you like work with, like when you're doing like geometry, and it's like if you don't have the examples, then it's just like a lot of theory, and then you don't know where to instantiate it. So yeah. So today, I guess I can impromptu talk about hyperbolic space. So let's talk about the hyperbolic plane. So what is H2? As a set, this is the set of pairs x, y, such that y is greater than or equal to 0. Alternatively, this is also isomorphic to the set. This is the D2. This is the unit disk. So what is hyperbolic space? I'll explain that later. What is hyperbolic space? So hyperbolic space is sort of an alternative to the usual Euclidean geometry that you're used to. So usually Euclidean geometry that you're used to, you have things like a triangle has all its angles sum up to pi. If you look at it on a sphere.
Wait, do you mean D2 without a point?
No, D2.
Wait, is it not like, you know, when.
Correct, but you also don't have an x-axis. Sorry, this should be greater than 0.
Oh, okay.
Correct. Yeah, my bad. Yeah, so if you draw like a triangle on a sphere, right? It'll kind of be like fatter than a triangle on a plane. And so if you like draw like the three-dimensional triangle which goes out of the sphere, then this will have its angles sum up to pi. Because here you're like inflating a little bit, this triangle on a sphere will actually have its angles sum up to a little bit more than pi. You can show that, we'll probably see this later, that the amount by which it is more than pi is actually related to the area of the triangle. It's pretty interesting. And hyperbolic geometry is sort of the third alternative to this, where you can draw triangles, and all the triangles will have an angle sum less than pi. And the amount that is less than pi is again proportional to the area. So instead of giving you like formal definitions of like, oh, here's a metric, here's like the metric for the hyperbolic space and whatnot, I'm going to instead draw a bunch of pictures and try to convince you that the geometry here is like, there's a lot of things which feel like geometry. So in geometry, you have lines, right? So what are the lines in hyperbolic space? If we use this upper half plane model, the lines will be semicircles, which are perpendicular to the x-axis. Okay, so this is one type of line. But what you can also do is like imagine the second semicircle moves further and further and further and further away. What will happen is that you can sort of imagine like the semicircle opening up and you get a vertical line. I realized that before I did this, I should give you some example of something else. So a sphere is positively curved, and we have this notion of curvature in geometry, where if you have something which looks like a dome or a bowl, this is said to be positively curved because this is like positive curvature times positive curvature is positive, negative curvature times negative curvature is positive. You can also have negative curvature, and the canonical example of a negative curvature thing is a Pringles chip. So a sphere is something with a uniform positive curvature, and curvature sort of like scales like 1 over r squared. So if you have like the tip of a pencil, right, that's curved a lot over a very small amount of space. So it has a very large curvature. If you consider like the same amount of curvature like on the surface of the earth, it's a very small curvature because it's like spread out a lot of space. So you can instead look at something which has a uniform negative curvature, and there is such a shape which kind of looks like this. So it's like you take I think it's like you take like an exponential or something, and then you sort of wrap it around something a bit more complicated. It's called a spheroid or something. Search up hyperbolic spheroid, you'll find it. And so what this does is it has negative curvature along this direction and positive curvature along this direction. So it has a negative total curvature. And it turns out that it has a constant negative curvature. So one thing that we can do is we can sort of like unwrap this guy. And if we unwrap it, what we're gonna get is something like this, where we have to like glue the ends together, right? If you like cut along here and like unfold it. So what we can do is we can sort of like distort this by stretching it out on top and make this into a strip. So what we've done by distorting it out up top means that if we draw circles of the same size over here, these actually aren't the same size over here. This circle will be very small, right? But then they'll get bigger and bigger as we go down because we've stretched this out. So to go back, we have to shrink it. So what this means is that the apparent distance up here is really small. The apparent distance down here is really large. And actually, there's apparently this edge that we see in this guy. Actually, we can extend further. So this corresponds to line y equals 1, but we can go even bigger. And the point is that this gets so big that it doesn't actually fit in Euclidean space, which is why we can't actually extend this further. But we can extend it further over here so that the distance from this guy to here is actually infinite. Because as you keep going down, the distance gets so much like stretched out that like it takes infinitely long to get there. Yeah.
Is the point you put on the bottom on the y equals 0?
On the y equals 0, yeah. So that's why we exclude the line y equals 0, because it's infinitely far away. So yeah, something like that. And what you can do then is like you have this awkward thing where you have like something cut off on both ends, right? So what you do instead is you like extend your cylinder by just putting a bunch of copies of it. And extend it down below to y equals 0, and what you end up with is hyperbolic space. So the geodesic over here, for example, so it looks like something which like winds up and then comes back down, right? So it's sort of like going up and going back down, so it's like winding up and then coming back down. And then the geodesic that goes up perpendicularly is like this straight line which goes up perpendicularly.
Are they tangent at the bottom?
They are perpendicular to the bottom. Well, actually, no,
That's
sorry. In this case, no, because this is the line y equals 1. So that would be like
Right.
this thing. Okay. Does that make sense? Alright, so let me start talking about the geometry of this guy. Sort of removed from this. So that was like sort of motivation for constructing this. But I'm gonna say now we're gonna use this as a starting point, that the lines are semicircles perpendicular to the x-axis or vertical lines. So what are some things that you want to be able to do with lines? Well, you want to be able to reflect across lines, and you want to be able to like translate across lines, for example, right? So I'm going to show you how those two operations work over here. So if you want to reflect across this line, what's going to happen is everything on the inside is going to go on the outside, everything on the outside is going to come to the inside. And there's an operation that does this, and it's called circle inversion. And so what it does is you have a circle, and if you have some point over here, let's call this distance r, then we have that x gets sent to x over r squared. And the reason for that is that if you do this operation twice, then you're going to get back to your starting point. So that's sort of like a reflection, right? So like you take this point, it'll go somewhere over here, and then if you apply it again, it'll go back in. And so what happens with circle reflection is like, as you get closer and closer to 0, because of this denominator r squared, these points will get more and more spread out as you invert them. And circle inversion has some surprisingly nice properties. For example, it'll send circles and lines to other circles and lines. So if you have a circle over here, it'll send it to another circle. If you have a circle which goes through the center of this circle, what will happen is that this point gets sort of like sent infinitely far away. So then this guy actually becomes a line after you reflect it. And it also turns out to preserve angles, and that's a sort of less obvious thing. But it turns out to be true. So what then happens is, like, let's say we reflect across this circle over here. What will happen is this circle will go on the outside and will sort of become like this guy. Yeah.
Wait, does it feel more obvious if you look at it from like complex numbers?
Yeah, so it turns out that, I don't think I have time to talk about it right now, but circle inversions correspond to something called linear fractional transformations. And these are holomorphic functions. And so because of the holomorphicity, it preserves angles.
Can you just think of it as inversion up to like a translation or something?
Yeah, probably. Yeah, so these can be generated by like looking at z goes to 1 over z bar, and then translations and scaling, and those generate everything. The reason for 1 over z bar is so that you preserve orientation. Or sorry, you reverse orientation, because you want a reflection to reverse orientations of things, right?
Oh.
So like if you have something like going this way, then the reflection should be going that way. Anyways, yeah, I don't want to talk about linear fractional transformations right now, but sort of the idea is that you can like invert along this line and sort of go from the inside to the outside. Does that make sense? Cool. There's this cool statement now that says like, if you have a line, right? Then if you have a point on this line, there is a unique perpendicular connecting it to that line, right? And this, okay, I'm like doing this without preparation, but I think I remember to prove this. The same thing holds over here. So what happens is, if you take any point, it turns out that there's a unique line that goes out of this point and meets this circle perpendicularly. And by line, again, I mean like semicircle which goes to the origin. And the way that you prove that is like, look at the reflection of this guy, right? And now you can consider a bunch of circles that pass through both of these points. So you can consider this circle, you can consider this special circle, you can consider this circle, right? And what happens is like, sort of through an intermediate value theorem, you can show that of these angles, there's exactly one of these circles which will intersect this one at 90 degrees. So to recap, what you do is you take a point, you look at its reflection, look at all the circles which pass through both points, and there will be exactly one that intersects at 90 degrees. And the cool thing is like, if you apply circle inversion, then this entire line is kept fixed. Yeah. And the reason that it's kept fixed is because angles are preserved, And so this 90-degree angle must be sent to the 90-degree angle, and so, yeah.
So you chose the circle that intersected 90 degrees, and the fact that this is actually a line, meaning it intersected at 90 degrees down there, is lucky.
Oh, that's a good question. I'll think about that and get back to you. Yeah. So now that's how you do reflections. Now what about translations? So let's say that you have this circle, and you want to do translations on the circle, which means like, so if you have a line, right, you can translate it along some direction, which says like if you point over here, move it over there, right? So if you have this sort of thing, that should mean like on the line, you move along the line, and then you want to move like sort of move the entire hyperbolic plane somewhat in that direction. And what you wanted to do is you want to preserve distances. And so what you can do is you can like pick this unique perpendicular line for every single point in the plane. And so what that'll set up is this sort of foliation of the plane into semicircles. Essentially vertical, and then something like that, right? Does this picture make sense? All these are perpendicular, and this will account for every single point in the plane. And so what you can do is like you can translate along these, and again, because like distances actually get more spread out as you go in, as you go down, what'll happen is like these lines will get more and more dense. So you translate this line to this line, this line to this line, this line to this closer line, this line to an even closer line, and so on and so forth as you go down. So this is how you translate things. But that's sort of, I haven't specifically told you how to translate because I haven't told you like what line to go to, right? I'll go like 5 minutes over for you guys, so I'm not because we started a bit late. But what you can do is like you can describe a translation in terms of reflections in the plane, right? What you can do is you can take two lines which are perpendicular, and you can reflect across this line and reflect across this line, and what that'll end up doing is translating across this plane. So if you like reflect across this line, you end up over here. If you reflect across this other line, you'll end up over here. So what this does is if the distance between the two lines is a, this will translate by a distance of 2a. So what you can do over here is you can take two of these lines, reflect across this line, reflect across this line, and so what that'll do is, if we call this distance a, again I haven't specified how to specify distance yet, but this will translate by 2a. And because reflecting across this line will preserve this angle, it will preserve the circle, and then same thing with reflection across this line. So that means that the circle gets sent to itself. Now there's an interesting question of like, what happens inside and outside the circle? So, let's see here. If you can visualize, if we apply this translation by a bunch of times, what happens to like this point? So like translation by a in like this direction. So like if this is on some line like here, it'll go to some line over here, some line over here, but it'll sort of stay on in the inside of the circle. So what'll happen to it after we apply a lot of translations?
It'll end up closer to this edge.
Right, so it'll like go, you'll end up like over there, right? Okay, so what happens if we translate it in the other direction? Okay, so it'll go like that. So the orbits of the orbits of translations in the plane is just straight lines, right? Do you have a guess as to what orbits of translations in this guy is going to look like?
Well, it's not a straight line because it's not.
It's not perpendicular to the edges.
Yes. Bent out.
Can you give a sort of non-hyperbolic description of what it is? Maybe a Euclidean description of what this trajectory is? I guess.
It's like curving.
What is curving?
The trajectory.
Well, this trajectory is curving
Never mind.
It's like a mustache. Is what he said.
now. Okay.
Like a circle of larger radius shifted down or something.
Sure, so maybe it's like a circle that passes through both of these endpoints, because that's what ends up with if you apply a lot of translations either way. And it has to go through this point, right? So that's your guess. And this turns out to be true because, like, you can describe translation as two reflections, and the reflections have to fix these endpoints where the circle intersects the horizontal line. And so since it preserves the circle, it fixes these two endpoints. And that means that because circle inversions also fix circles, it also has to send this circle, has to send it to itself. Forget the intermediate detail, but there is some other, yeah. I think if you like look at this angle, it has to preserve this angle as well. And so it'll have to send the circle to itself. And the reason it has to preserve the angles because if you look like really close to like over here, basically the translation will be linear and it will be linear like along that angle. So it has to preserve these 2 points of intersection, it has to preserve the angle. And a circle is specified by the 2 points of intersection with the angle of a line that's intersecting. And so it has to preserve this whole circle. So what that means is that any point on the circle has to be sent to another point on the same circle. So that's a pretty cool description. And what this means is like translations should fix things which are equidistant from this line. So the points which are equidistant from this line correspond to not hyperbolic lines, but like Euclidean circles, which pass through those points. And so like if you look at the ones on the outside, like these are also points which are equidistant from the single line. And the last little thing that I want to talk about is like, you could translate this picture into the plane. So what you do is you like essentially collapse this whole circle down. So if we call this like 0, 1, and then up here we have sort of a point at infinity where the vertical lines go up to infinity. Then we sort of compress this down into a circle where then this is 0, 1, and infinity. And so what lines look like over here is, again, semicircles which are perpendicular to the boundary. And the way you do this is some linear fractional some other circle inversion through like this sort of circle. We can talk about the details after if you want. But you end up with this circle, and this is another model of hyperbolic plane where now lines are these semicircles which are perpendicular to this boundary of the unit circle. And the vertical lines are nothing special anymore. They're just lines that pass through infinity. Or you can also have like horizontal segments. And so what happens here is like, let's say you want to translate about this line. This will fix this line, but sort of like, these circles I just drew get translated into circles that look like this, right? So translation along this line, for example, will sort of move along these circles. Sort of reflection along this line, for example, will exchange the inside and outside of this circle, and reflection across this line will like sort of just flip these two things. So one nice thing that you can get from this picture is the isometry group of the plane, right, is translations plus rotations. You get the isometry group of this guy really easily. And what you do is you take any point, and it turns out you can send any point to the origin. And the way that you do that is like just draw the line from the point to the origin and then translate across that line using a hyperbolic translation. Okay, so what that means is we have some group which sends points here to the circle. And if we look at what the fixed point of, all the transformations that will fix the point at the circle, what we end up with is that it has to preserve, this is a radially symmetric picture, so all of these points are equidistant from the center point. And so we have that the only things that fix all of hyperbolic space and this point are rotations. So it turns out there's a 3-dimensional space of symmetries, 2 dimensions because you can take any point to the origin, and 1 more dimension for the rotations about the origin. And this gives another cool interpretation because this is point equidistant from this point over here, right? The circle, because of the rotational symmetry of the picture. So if we translate back to over here, what will happen is we get another circle over here. Well, this will be sort of a distorted circle. This won't have the center as the same Euclidean center, but this is a circle with hyperbolic center at this point. So these are all points which are equidistant from this point, and this sort of gone by translating this guy back across. So this is cool because if you consider circles which don't intersect the boundary, they're equidistant from a point. If you consider circles which do intersect the boundary, they're equidistant from some line. So that's a pretty cool picture. And this hints at some sort of a duality between points and lines in this space. Yeah, that's my introduction to hyperbolic geometry. Later on, hopefully we can talk a little bit. The reason I want to talk about this at some point was examples for when we start talking about curvature and whatnot. There's like sort of 3 different nice examples that you can work with, which is the plane, the sphere, and so the plane gives you, it turns out there's some things called like flat tori. Sphere has constant positive curvature. It turns out any homogeneous surface, you can make it into a constant negative curvature shape. So I want you to sort of like see this sort of thing so that we can talk about that later. Any questions on hyperbolic space? Yeah.
Can you draw a triangle for me?
Yeah. So here it's like kind of interesting, right? So, wait, let's see here. So this is one line. Here is another line, and here is, let's extend this one out. So this, maybe something like this, right? So then this forms a triangle.
I see.
And so it turns out that the angle sum is going to be less than 90. You can have some interesting things here, because you can sort of draw things which are like triangles. They're called ideal triangles. Something that looks like this. So what happens here is like, first off, because
There's no angle.
yeah, the angle is 0, right? But the thing is, like, the vertices aren't actually in the space. So these are called ideal triangles, and the angle is 0 over here, which
Does that sound ideal to you?
it does sound ideal to me. I like 0. So
Can you draw that in the other?
yeah,
Oh yeah. Not about the triangle.
or alternatively, you can make it like this. Yeah. So
I learned from Squid Game that that's actually called an umbrella.
no, that one you need a little. Yeah. But it turns out that because angles are, we'll see later that angles are related to areas, that all of these have the same hyperbolic area. Any other questions?
What is can you embed flat torus in R3?
No.
R4?
Yes. Exercise.
Don't make me ask it. You?
Wait, it's really simple. Like, take 2 copies of R2, put a circle in each.
Oh.
Other questions? Turns out that ends up being